Right, welcome guys. Yeah, still trying to fix things. All right, can you guys confirm that you can see my screen as well as you can hear my voice clearly?
I can see your screen and hear your voice. Yeah.
Okay, very good. Okay. Would you also please alert me if somebody joins the Zoom? Last time somebody tried to join the Zoom and I wasn't paying attention, and so I couldn't let the poor guy in.
Okay.
All right, okay, so we'll start. Let me see. All right, okay. Oh, people are still coming in. Admit them. All right, okay. Is everybody ready? Okay, so I'll start as again, if some people get in, just keep a watch and just let me know. Right, so let's start from where we stopped last time. So we were talking about, I'll go back in the notes. So let's have a quick review of where we ended last time. So we talked about Brunner's theorem, which is a fundamental theorem in quadratic optimal transport, which says that if I'm trying to transport mu to nu on RD with the quadratic cost, and assuming that mu has a density, then there's a unique solution to the both Monge and Kantorovic's problem, and that unique solution is given by the gradient of a convex function. Then we talked about, okay, the gradient part is not so important. It's really a subdifferential that we're talking about. And then the important thing that is that once we have Brunner's theorem, we can talk about not just a terminal transport, but an entire curve of probability measures, which are all the intermediate points. And how is this defined? It's by the following formula that if I have my Brunner map T of x, then instead of going all the way to T of x, I will go intermediate points. I will take 1 minus T identity plus the T of x, and that gives me some intermediate point of transport. That is what I call T of x. And this capital T of x, if I push forward my initial measure, then I get my rho T, which is my McCann interpolation or the geodesic in optimal transport. By the way, here's a question for you guys. Okay, somebody is here. All right, okay. So here's a question for you guys. So clearly, this map of T of x is push forwarding that takes my mu and outputs rho t, right? By definition, my rho t is the one that I get from push forwarding mu by this map T of t. But is this transport map, capital T of small t, optimal? This is what you would expect from your physical intuition, right? If I'm optimally transporting particles from mu to particles from nu, and that optimal transportation is happening along straight lines, then of course at every intermediate point, I would get an optimal transportation. Why would it not be? But how do I see this? How do I see that capital T of small t, which is a transport map that takes my mu to rho t, is itself optimal?
You see if it minimizes the kinetic energy.
There's an easier way to see this. How do I check that a transport map is optimal? If I have any map which transporting mu to some other measure, how do I check that this is actually optimal for the quadratic cost?
I'll use Bernoulli's theorem.
Exactly. So you have to verify whether this is a gradient of a convex function or not. And so you have this formula for T of t. Is there a convex function that you can find for which this is the gradient? What do you think? Is this question clear to everybody? So I want to check that my physical intuition says that all my intermediate transport should also be optimal. In particular, capital T or small t must be optimal, but then it must satisfy Bernoulli's theorem, which means that it must be the gradient of a convex function. What is that convex function? So capital T is already a gradient of a convex function. Any answers here?
If you look at 1 minus t times 1/2 norm of x squared plus t
Very
times
good.
speed.
Exactly, Bashir is correct here. So it is 1 minus t, 1/2 norm x squared plus t of p of x. Then I get capital T of t is the gradient of phi of t. That's exactly correct. The identity itself is an optimal transport map. It is given by the gradient of 1/2 norm x squared. And the other map is given by the gradient of phi. And convex functions are preserved under taking convex combinations. And so when I take the convex combination of the two, I still get a convex function. And the gradient of that gives me T of t. So it conforms to my intuition that every intermediate transport is also optimal. It has to be. Otherwise, if there is some slack there, I would be able to improve my full transport. Is this clear? Good. So then we went about idea of defining a geodesic. And so we said that why is Macan interpolation also a geodesic? It's because it minimizes kinetic energy. You define your dynamic optimal transport over oval paths, and then you define the cost of a transport to be the kinetic energy, and then it minimizes this kinetic energy. And that's where we basically stopped. And so now we come to this other important definition of a geodesic, which is called a generalized geodesic. Sometimes geodesics in Washington space are not optimal to work with, pardon my pun. But there is another concept of a geodesic. They are called generalized geodesics. This is another useful of a curve. I'm calling them geodesics, but you should really think of them. There is a geodesic property of them, but you should really think of them as drawing curves on the space of probability measures. Now, these generalized geodesics are not geodesics. They depend on a certain base measure, which I'm going to fix rho. So rho is a probability measure, which is AC, which means that this is absolutely continuous. So it admits a density. And there is a certain there's a certain abuse of notation which is very prevalent in this theory, which is that when I work with absolutely continuous measures, I denote the measure as well as the density by the same notation. This is followed in all papers, all textbooks, and I'll follow it in these notes as well. So when I say rho is absolutely continuous, rho can refer to both the measure as well as its Lebesgue density. Now, I have two, so rho is here, and I have two other probability measures. One is mu, and the other is nu. And I want to draw a curve between mu and nu. I want to draw a curve between mu and nu. How will I do this? I take my Brunier map that sends rho to mu, and that's my T0. So T0 is a gradient of a convex function which push forwards rho to mu. Why does T0 exist? Because I've taken rho to be absolutely continuous. Typically, in this case, rho is taken to be either normal or uniform over a ball or something like this. But that's beside the point. Any absolutely continuous measure will do. Then there exists some T0 which will push forward my rho to mu. There will exist some T1 which will push forward my rho to nu. And now I define this intermediate transports, which is a convex combination of these two. So it's 1 minus t T0 plus t times capital T1. And I define my rho t to be the push forward of rho by this capital T of t. And this curve is called rho t. This curve are all these intermediate densities or probability, not densities necessarily, but intermediate probability measures that I get from this construction. So this is called a generalized geodesic with base rho connecting mu and nu. If you change rho, this curve will change. So the base is very important. But the idea is very similar to McCann interpolation. Does this make sense? Same question. Rho t is given by a push forward of rho by a map capital T of small t. Is this map optimal? Same question. Is this map that I'm getting from rho that is push forwarding rho to rho t, does this satisfy Brunier's condition that this is a gradient of a convex function? The answer is yes, because by my assumption, T0 is optimal. It's actually the gradient of some convex function phi0. T1 is optimal, is a gradient of some convex function phi1. And therefore, by T of t is the gradient of the convex combination of these two convex functions. So it's 1 minus 2 phi0 plus t times phi1. And this is convex. And therefore, this transport is optimal. Good. So again, nothing crazy is happening. We are just drawing curves from one point mu to another point nu. Sometimes I just follow the McCann interpolation. Sometimes I have a third point rho, and then I will draw these curves. So they should be thought of as like drawing straight lines, depending on the context. Let's see some examples. So here is an example. So I take my base rho to be normal 0, 4. My point 1 corner of the triangle mu to be normal 0, 1. And the other corner of my triangle nu to be normal 1, 4. Good. Now, as I explained last time, optimal transport of Brunier's theorem between normal distributions is very easy to compute. They're always given by affine functions. What is the affine function that you pick? The one that gives you the correct mean and variance. So it's very clear that T0 that sends rho to mu must be 1/2 of x. because you take normal 0, 4, and you divide by 2, you have the mean 0, you get variance 1. T1 of x must be x plus 1, because you take normal 0, 4, you add 1 to it, you get normal 1, 4. And so all the intermediate points are going to be 1 minus t of x plus t times x plus 1, which is just 1 plus t over 2x plus t. And so I get rho of t is the push forward of normal 0, 4 by this affine map, and it comes to normal t 1 plus t square. I've done this computation in the last class. You'd be able to find in the previous slides that this is also the actual Macan interpolation of the geodesic. So in this case, the generalized geodesic and the geodesics are the same. And this can happen. This is a special case of the normal family of distributions where everything is super nice. That's why people like normal distributions, where this gives me the same answer. Is this clear? My next example will show that this is not always the case. But everybody understands this simple example here? Okay. So in my next example here, I'll show that the generalized geodesics need not be actual geodesics. So as long as rho is absolutely continuous, my generalized geodesic always exists because Brenner's theorem holds, and therefore I get my T0 and T1. So here I take a very common choice for the base rho to be uniform 0, 1. So I'm in the real line, and my base is uniform 0, 1. Now I take my mu to be the delta mass at the origin, and my nu to be this Bernoulli random variable, one half Bernoulli, right? So this is my, in probability language, this is my Bernoulli 1/2, or binomial 1, 1/2, if you wish. Now, mu is purely atomic. It has exactly one atom, which is the origin, and therefore Brenner's theorem does not hold. So there is no Macan interpolation that takes delta naught to this Bernoulli 1/2 random variable. It doesn't exist. But the generalized geodesic always exists because rho itself is absolutely continuous. And so my rho, which is push forwarding my uniform to the mu, which is delta of 0, well, that is, of course, just send everything to 0. So generate a random variable from the uniform, image is 0, the whole mass goes to 0. My T1, and again, this is something I discussed in my last class, is the indicator of x greater than 1/2. So generate a uniform random variable. If it is larger than 1/2, you say 1. If it is less than 1/2, you tell 0, and that gives you Bernoulli. Right? So this is easy probability. And so if I take the convex combination of T0 and T1, I get my Tt of x is T times indicator x greater than 1/2. And so what is my rho T? This is 1/2 delta 0 plus 1/2 delta T for T between 0 and 1. So look at this beautiful curve that I'm getting. So I am here and I want to go here. So I'm here, which is my full mass 1 at the origin, and there's nothing anywhere else. I want to go here, which is half a mass at the origin, half a mass at 1. And what are my intermediate steps? Half a mass at the origin and half a mass at t. So I just split the mass at the origin to half a mass, and I just move the atom continuously from 0 to 1. And that's all my intermediate property measures. Makes complete sense. Again, it preserves shapes, it's intuitive what I'm doing, and it makes complete sense. And here you see generalized geodesics are beautiful because the geodesic itself doesn't exist, but this curve is nice and natural, and I can always create it. Everybody is with me? Good? All right. Now, I keep on saying that this is a generalized geodesic, and I should be able to justify it. Again, in what notion is this a geodesic? So I justified that Macan interpolants are geodesic because of this notion of dynamic optimal transport. They are curves that minimizes total kinetic energy. So in what sense is what sense is generalized geodesics also geodesics? It has to do with what is called a linearized optimal transport. Now, this is a concept again which has become popular due to some applications in machine learning, which we cannot get into. But if you search online, you'll get several recent papers that does linearized optimal transport. So what is linearized optimal transport here? 1 second. Oh, okay. Give me 1 second. This is not my. Okay. That was the older version of the file. Okay, what happened here? 1 second. Okay, I've messed up something. Hold on. Oh, there are more people here. Give me 1 second. There's something I need to check. I need to download the latest version. Fine. All right, let's see now. Yeah, okay, good. Now I'm in the correct file. All right, okay. So in what sense is the generalized geodesic an actual geodesic? And so that's the question. So this is this is definition of generalized geodesics. In what sense are they actual geodesics? The idea of it is that it's linearized optimal transport. I don't know why I've written linearized. It's really linearized. Not linearized, but linearized optimal transport. So what is a linearized optimal transport? So what you do is that once you fix this base probability measure rho, with respect to which everything is being computed, and you look into any of these Brenier maps, T0 and T1, that push forwards my rho to mu and nu, then they are in L2 of rho. Why are they in L2 of rho? Because I am assuming all my measures have finite second moment, and T0 push forwards my rho to mu, T1 push forwards my rho to nu. So this L2 of rho is a Hilbert space, and all these Hilberts on this Hilbert space of functions, I have these two functions, T0 and T1. So I can define a metric by using my Hilbert space metric. So I can define how different are the two probability measures mu and nu. And I say, well, let's look into the L2 norm between T0 and T1. Is this clear? So again, let's go back to this setup here. So here is my rho, which is my base. I have my mu, I have my nu, And rho is pushed forward to mu by my Brownian map T0. Rho is pushed forward to nu by my Brownian map T1. And then I join between mu and nu by my generalized geodesic. The point here is that both T0 and T1, they are both members of L2 of rho. And this is a Hilbert space. Over the Hilbert space, there is the usual L2 norm. And so I can measure how different T0 and T1 is according to the norm of the Hilbert space. And I can define a distance between the probability measures mu and nu by using that distance between T0 and T1. Is this a good norm? Yeah, of course, because I'm getting using my L2 norm from this. Of course, it's a good norm. If it is 0, if and only if T0 is equal to T1, in which case, of course, mu is equal to nu because I'm push forwarding rho by the same function. The benefit of this is that L2 of rho is a very well-studied Hilbert space. And over the Hilbert space, I know that I can define geometry which are straight lines. And that's a straight line which is a generalized geodesic. And these straight lines are my generalized geodesics, joining mu and nu. The problem with this aspect is that, okay, I have to pick a rho, which is kind of arbitrary. What do I pick rho? You might like normal 0 on. I might like uniform. There is some confusion there about what is the base, right base. And depending on the choice of the base, the whole geometry will be different. There are also flat geometry because Hilbert spaces are flat. And so there are things that don't quite get captured there. You should kind of think of this Hilbert space, like we will come to this, the Wasserstein space in the next slide. The idea being that the Wasserstein space is an infinite dimensional Riemannian manifold. And you should really think of this linearized optimal transport, this Hilbert space, as something like a tangent space at rho. And that's the right way to think about it. We may or may not come back to this intuition later, but this is an important concept. In this concept, generalized geodesics are actual geodesics in this Hilbert space. Good. Any questions? All right, okay. So now we come to the actual Wasserstein space. So the actual Wasserstein space is, what is this object? So I'm going to fix RD as my base space over which all my probability distributions are situated. My set of probability measures with finite second moment, that's what I'm going to always denote by P2 of RD. Now this P2 of RD, this is a set of probability measures. It's a set of all models, all data. I'm going to first turn it to a metric space. And what is my metric there? This is my Wasserstein 2 metric. So this is the Wasserstein 2 metric. This is the OT cost for the quadratic cost, so x minus y norm square of transport. Okay, so for any two probability measures, mu and nu, look at all the couplings, that minimizes the quadratic distance between x and y. Whatever is the infimum, that's what I call my W2. It is actually a metric, and I get that my space is actually a complete separable metric space. And on this metric space, I've turned my probability, this finite, all probability measures with finite second moment, to a metric space, to a nice metric space with this metric. This metric space is of paramount importance for the rest of the course, and it's sometimes called 2 Wasserstein space, sometimes it's called Wasserstein space, sometimes it's called just Wasserstein 2 space, a number of names. They all involve the word Wasserstein, there's a funny story that there's a mathematician whose name is Wasserstein, who is still there actually, I think in Penn State or somewhere, who by the way has nothing to do with optimal transport or Wasserstein space, but due to some weird nomenclature of mathematics, his name gets forever associated with Wasserstein space, this very important concept. He has done other important things, but nothing to do with the Wasserstein space. Anyway, so this is a complete separable metric space. We are also going to focus sometimes on a particular subset of this P2 of RD, and this subset is a subset of absolutely continuous distributions, and which I'm going to denote by P2AC. Now, one thing that I should say here is that what is a topology in this metric space? What is a topology in this metric space? So I have a metric, and the matrix obviously gives me a topology. So what this means is that mu n converges to mu if the Warschachtine distance converges to nu. But there's an easier description of this topology which doesn't require computing the Warschachtine space together. And the topology can be described in the following way, which is you say that mu n converges to nu if and only if 1, mu n converges to nu weakly, which is, I think this is what Young was saying about weak star topology, but in probability we just say weak topology. So it's just weak convergence. And 2, the moments converge. The first two moments converge. So the second moment convergence. Okay. So if you want to check that a sequence mu n converges to nu in this metric space, the Warschachtine space, you have to first prove that there is weak convergence or convergence in distribution. This is, of course, the bread and butter of all statistics in probability. And then you have to prove that the first two moments, essentially enough to show that the second moment actually converges, which means that the variance and the mean converges. So if the mean converges, the variance converges, there's convergence in distribution, you have convergence in the Warschachtine metric space. This is by no means a trivial theorem. This is actually a deep theorem, but this theorem is true. Is this clear? So the metric sphere, all probability measures with finite second moment, is turned into a metric space by endowed by the Warschachtine 2 metric. This metric is, of course, abstract. So, but we would like to know when there is convergence, the topology, which is weaker than the metric. And there's a very useful characterization of the topology. The convergence of mu n converges to nu if and only if 3 things happen, which is that you have convergence in distribution, and then there's convergence in mean, convergence in variance, or covariance. So convergence in distribution. As you can see, I still haven't managed to get good in using my iPad, but I'm getting there. So convergence in distribution, convergence of mean, and convergence of covariances. And these 3, they are equivalent, and they're equivalent to the convergence in this Warschachtine space. Anybody needs any explanation on the notation or the definition of any of this? Are you familiar with these concepts?
Yes, I'm from
Okay.
physics background, so I'm not sure. What are you denoting with mu sub n?
So this
What
is
is the
some
endpoint?
sequence in P2 of RD. This is a sequence
Oh,
of
okay.
probability measures. And I'm saying, when does a sequence of probability measure converge to another probability measure in this metric space?
Okay. Okay.
And
Thank
so
you.
what I'm saying is that you don't have to compute the Warschachtine norm at every step. You don't have to do that. You just have to
Right.
compute 3 things, which is convergence in distribution, convergence of mean, convergence of covariance.
Right. Okay. Thank you.
Sorry, somebody's asking, if possible, can you discuss briefly what? Can you be more explicit? Just briefly, what do you want me to discuss briefly?
No, I mean the convergence in distance and convergence of mean, and I mean these definitions just.
So convergence in distribution is what Young said is a convergence in weak star topology. So this is a standard definition where you say that mu n is converges to nu, where the integral of f d mu n converges to integral of f d mu for all f which is bounded continuous functions. So that's convergence in distribution. So this is convergence in distribution.
Okay, Professor, maybe I started these things in measure theory.
So in measure theory, you would call this to be weak star convergence. But in probability or statistics, this is called weak convergence or convergence in distribution. What does
Okay.
convergence of mean mean? Well, for every mu n, you can compute the mean vector. This is the average, the mean vector. So that's a sequence of vectors, and this is a usual Euclidean sequence of vector convergence. What does the convergence of covariance mean? Well, for every mu n, you can compute the covariance matrix. Well, that's a d by d matrix of real numbers. And again, convergence means that pointwise for every cell of this matrix, they converge. So you verify these three convergences, you have convergence in Warschachten space. Makes more sense?
Okay, okay. Thank you.
All right, great, good. All right, okay. Now we
Sorry,
come
I
to
have
the, sorry, go ahead.
I have a question. So, I guess we were kind of given a sequence implicitly. Oh, sorry. We were given a sequence implicitly by this row, and you're saying that we can figure out if the push forward of row, I guess, converges.
I'm
or
sorry,
sorry,
no, where are you? There is no row in this. Are you
no, I
talking
was
about
from the
here?
previous slides, yeah.
From the linearized optimal transport?
Yeah, I was wondering,
Okay.
yeah, and the discussion before, I was wondering if there's a connection between the generalized geodesics and the convergence in the Wasserstein space.
Yes and no. So, okay, so there's yes and no. So look into this. Maybe this picture is actually easy to understand. So rho is being sent to mu by T0. Rho is being sent to nu by T1. Suppose T0 is invertible. Then I can go from mu to rho and then follow T1 to nu. And so if I'm given T0 and T1, I can get a transport map from mu to nu, which is from T0 inverse T1 composition. This may not be optimal, but if this converges to 0, for example, for a sequence, then I also have convergence in the Warschachten space.
Okay.
But it's not they're kind of related, but I wouldn't like try to prove convergence in one using the other. They don't always go well together.
I see.
But sometimes
Okay, thank
you can. Any other questions? So again, I want to stress that this metric, the linearized optimal transport, and this metric, the Warschachten space with the Warschachten metric, I'm putting two different metric structures on the set of finite probability measures with finite second moments. In fact, they have entirely different geometries. We will very soon, in the next class, next week, we will see that the Warschachten space can be thought of as an infinite dimensional Riemannian manifold with a curvature, with a positive curvature. They are entirely different geometric structures, but in that positive curvature space, you should think of this linearized optimal transport as my tangent space. All right, okay. So next we come to the other important definition, which is convexity. So I'm going to stick to this. I'm going to stick to the Warschachten space for the remaining, in fact, for the remaining course. This is our main goal, to study this Warschachten space. And so one of the ideas is that, okay, how do I define functions of probability measures that are convex in this Warschachten space? So if I have a Euclidean space, I know what is convexity, and the definition of convexity depends on being able to draw a straight line. If I have a Euclidean function, it is convex, is f of 1 minus tx plus ty is less than or equal to 1 minus tf of x plus t times f of y, right? This is the definition. What does this definition depend on? Well, if I draw a line between x and y, and that line segment, the function restricted to that line segment is convex, right? This is my Euclidean definition. The Euclidean convexity has the following definition, that f is convex if and only if I take any x and any y and draw a line segment joining x and y, and if I restrict f onto this line, then this is convex on this line. For all x and y, this has to be true. And then f is convex, right? That's the definition of convexity. So if I try to generalize from this definition, my natural definition of convexity would be, well, if I take any measure mu and nu, take any mu and any nu, and I draw my McCann interpolation from mu to nu. And that's my rho t curve. If I have a function f from all probability measures to real line including plus infinity, I say that this is geodesically convex if this function restricted to this, all of these geodesics, is a convex function of one-dimensional parameter. So f of rho t, this is convex. Okay. Sometimes it's also called displacement convex. Sometimes it's called geodesically convex. They are the same thing. But is the idea clear? So I have a function over all probability measures. How do I say that this function is convex? Well, take any two probability measures, mu and nu, and draw the geodesic curve between the two. That's a one-dimensional curve, right? It's indexed by t between 0 and 1. So if I restrict my function over that curve, I get a one-dimensional function that takes a number between 0 and 1 and outputs f of rho t. If this one-dimensional function is convex, for every such geodesic, the function is convex. Good. Being absolutely continuous is actually not important there. There's a way to generalize this. It's just more complex notationally. So I'm always going to restrict myself to absolutely continuous probability measures where these definitions are just simpler. Are you guys clear about the definition of geodesic convexity? So the function is convex if it's restricted to every geodesic is a convex function of one-dimensional parameter. Okay, so what about generalized geodesic convexity? Sometimes actually this one is important.
Could you,
Well, I
to
see.
make it more concrete, I'm just trying to think of our normal case where we had the what is it called? The
McCann interpolations.
McCann interpolant was also a normal.
Yes, I will give several examples. Let me just finish the definitions. So what's a function which is generalized geodesic convexity? So a function over all probability measures is generalized geodesically convex if for all base rho and any 2 points mu and nu, if I look into the generalized geodesic with base rho connecting mu and nu, then this one-dimensional function t to f of rho t, that's a convex function. Okay, so same deal. What curves I'm considering is changing, but otherwise it's exactly the same. I'm looking into either plain vanilla geodesic connecting mu and nu, and I'm looking into this one-dimensional curve, or I'm looking into generalized geodesic connecting mu and nu, and I'm looking into this one-dimensional function. Let's see examples here. My first example might look simple, but it's actually quite important, which is the following. Take a function v from Rd to R2 plus infinity, and assume that this function is convex. And now define my function of a probability measure mu to be the expectation of v under mu. Nothing simpler. I can take the mean, I can take the squared moment, I can take moment generating functions. All such functions, they look like this. You take a particular function, you integrate with respect to mu, and you get a function. The result is that if v is convex, then this function is both geodesically convex and generalized geodesically convex. If v is strictly convex, then this function is also strictly geodesically convex. By the way, what is a strict geodesically convexity? That's basically when all these one-dimensional functions, these are strict. These are strictly convex. Good. Now, I want to stress that there is a natural way that you can draw curves between probability measures. If I have two probability measures mu and a probability measure nu, a natural way is to take what is called a mixture distribution. So what is a mixture? You toss a coin if it is with probability heads, of the probability of heads being t. If it is heads, you pick nu. If it is tails, you pick mu, and you just draw a curve, which is just a linear interpolation between mu and nu. Now, this curve, which is widely used in lots of places, if I apply this function, which is just a linear function, I simply get this linear quantity. This is not strictly convex. There is no convexity, it's purely linear. And yet, if I use my McCann interpolations, my geodesics, and if I take V to be strictly convex, my function f is actually a strictly convex function of probability measures. Good. Is this distinction clear? This distinction is the core of why McCann interpolations are so powerful in applications and not the mixture models. Mixture models have other uses, but when it comes to doing geometry or optimization, they are not your friend. Okay, how do I check this geodesic convexity? I want to go through this proof because the proof is very short and very instructive, because that's how you prove geodesic convexity of every other functional, no matter how complicated. It's by replacing rho t by just one single random variable. So how do I prove that this function, which is the integral of vx mu dx, this function is actually convex if I look into a geodesic? So here is a one-line argument. So I have mu, I have nu, and I'm drawing the geodesic between mu and nu. So take a random variable x that is sampled according to mu. Now, capital T is my Brunier map that is transporting. Capital T is my Brunier map that is transporting mu to nu. So then, by my definition, if I look into this random variable, which is 1 minus tx plus t times capital T of x, that has distribution rho t, which is the tth element of my McCann interpolation. Okay, so again, spot the difference. My usual mixture model will take 1 minus t of the one measure and t times the other measure and do a mixture of the two. My McCann interpolant will sample a random variable from the initial measure and then consider 1 minus tx plus t times capital Tx, where capital Tx is, according to Brunier map, where it is supposed to be at time 1. That is distribution rho t. And so if I consider what is the function f at rho t, well, that's the integral. So this is my integral of vx rho t dx. But that's just the expectation under rho t of v. And therefore, this is nothing but the expectation of v of 1 minus tx plus t times capital T of x. Right? What have I done? I've done a change of measure. Instead of writing the things in terms of rho t, I've pulled back and writing everything in terms of a random variable x, that is distribution mu. But now immediately, if v is convex, I see v of 1 minus tx plus t of tx must be smaller than 1 minus tvx. This must be smaller than 1 minus tvx plus t times v of tx. This is where I'm using the convexity of v. And now I put expectations. I get this is 1 minus t expectation of vx plus t times expectation of v of tx. But x is coming from mu, so expectation of vx is f of mu. Tx has distribution nu, and so expectation of v of tx is f of nu, and therefore I get convexity of f restricted to this geodesic. Please understand this basic argument carefully. This is the simplest situation. This is where this argument is misapplied. Every other situation, the argument is basically the same. What you see here is this general philosophy that Wasserstein space lifts the geometry of the underlying space to probability measures. How does it do it? By Brunier maps. Is this proof clear?
Yeah, this is a very simple proof.
Good, good. Very simple proof, and that shows that this function is geodesically convex. Okay, here's a question. Take all probability measures in P2 of P2 of R, such that the mean is between -1 and 1, and the second moment is between 0 and 1. Is this set of probability measures convex in the Waterston space? And here, why convex means geodesically convex, which means that if I take any 2 points in this set, and if I draw a line between the two, do I get draw the geodesic between the two? Does it contain? Is it contained inside the set calligraphic? The answer is yes. This is indeed geodesically convex. Why? Because both these functions Vx equals to x and Vx equals to x squared, they're both convex. And so this function is a geodesically convex function of mu. This function is a geodesically convex function of mu. And I'm looking into a convex set of values, -1 and 1 and 0 and 1. And therefore, I look into these intersections of these two convex sets, and therefore it remains convex. Good. So from functional convexity, I can go to convexity of sets by simply restricting myself to a range which is convex. Is this clear? How do I see that my potential energy is also generalized geodesically convex? Same argument. Again, this basic argument, as I said, gets repeated in every single proof. So I want to prove that my potential energy, which is the integral of Vx d mu x, is also generalized geodesically convex. How do I see this? Well, fix my base rho, fix mu and nu, and now my curve that is joining the two is this curve, 1 minus t t0 plus t t1 push forwarding rho. And so same idea, if I compute my function at f of rho t, this is given by an expectation of v of 1 minus t t0x plus t times capital T1 of x, where x is now sampled from my base measure rho. And now by usual convexity of my function v, I get this. If v is strictly convex, I get strict convexity. If v is not strictly convex, I may not get strict convexity. Easy peasy. Good. Now let's consider is this really necessity? Is this really necessary? Do I need to assume v to be convex for this linear function, for this this potential function to be geodesically convex? The point is that you have to assume something. So here I have a counterexample of a function which is not geodesically convex. So let's see this. Take mu to be normal 0, 1. Take nu to be normal 1, 1. I already know how to compute geodesics between two normals, and in this case, this is just normal t comma 1. Right? Take my function Vx to be indicator of x positive. Very, very easy function, indicator of x positive. So it's positive, it's 1 when x is positive, 0 otherwise. And so if I compute what is f of rho t, so rho t is normal t comma 1. So if I sample my z from normal 0 comma 1, then this is just expected value of v of t plus z. And so that's a probability that z is greater than minus t, which is nothing but the Gaussian CDF, the standard normal CDF phi of t. Right? Z of minus z greater than minus t is the same as z less than or equal to t, and therefore that's capital phi of t. This is a standard normal CDF. So what happens if I take the derivative? I get this normal density, which is this object, 1 over square root 2 pi to the power minus t squared over 2, which is decreasing in 0, 1. Because, right, the Gaussian density is decreasing as you go on the right-hand side. But if this is a decreasing function, then this function cannot be convex. In fact, the function must be concave. And so this function, which is capital F, which I get from integrating this object, which is this indicator of x positive, cannot be geodesically convex. I've just exhibited a geodesic over which this function is concave. Good. Does everybody understand this counterexample here? So we need some assumption on the potential, and the right assumption is that it must be convex. Okay, all right. Now let's go to another class of examples. So here is another example, which is that given a function w, so I want to compute this following object, which is a function of mu is that integral of wx minus y d mu x d mu y. In the usual parlance, you should think of it as like a quadratic function of a probability measure. In fact, if I sample two IID random variables, x and y, these are IID from mu, then this is nothing but the expected value of w of x minus y. Right? Now, if this is geodesically convex, I should say here, if w is convex. So this function, this is sometimes called interaction energy function. This function is geodesically convex, or also generalized geodesically convex, if the function w itself is convex. Now, where do these functions appear? Some of the appearance of these functions come from physical models. So there is this particular function w, which is 1 over norm of z to the power the dimension minus 2, which comes from this repulsion potentials, which called Coulomb interaction. It's a very, very common physics model in which it comes. Some of these functions, like norm z to the power 4, they come from attractive models. They're coming where these particles are coming, when they're attracting each other. So this is a very common interactions in physical models. They also come in statistics. You may have heard of this very common model estimates in statistics called U statistics and V statistics. So V statistics are actually this one. So here I've seen, so if I take my mu to be an atomic measure, which puts mass 1 over n atoms, x1 to xn, then this is what is a typical V statistic looks like, which is 1 over n squared w of xi minus xj, where the sum is over all the atomic pairs xi and xj. This is what the V statistics looks like. Here's a famous example. Take wz to be 1 over 1/2 z squared, in which case my f of mu is 1 over 2n squared, double sum xi minus xj squared. And if some of you know some statistics, you will know that this is an algebraic manipulation, that this just gives you sample variance. It's 1 over n summation xi minus x bar squared, up to a constant, because it's usually 1 over n minus 1. So a very, very common example of things that you use in statistics, which is a sample variance, is actually one such example. Are you following this? Has anybody seen this thing that 1 over 2n squared xi minus xj squared is actually just a sample variance?
I don't think so.
Okay, so this is a very common identity. Okay, in 5 minutes you should be able to prove this by just plain algebra. Okay. It makes sense, right? You're basically picking two independent elements and comparing how distant they are. Well, it has to be related to the variance. Good. So there are many, many common examples of such things which are of this interaction energy, and therefore you want to know when is this actually geodesically convex. And this is a fact that I mentioned. If W is convex, then F is geodesically convex. So again, I want to emphasize this short proof here, because later we'll go to a more complex situation where this proof I will not be able to give full details of it. So if I take mu and nu, and if I join rho t to be my geodesic joining mu and nu, how do I actually compute what is f of mu? Well, as I said, just sample x, y, IID from mu. And then my f of mu is nothing but the expected value of w of x minus y. How do I get f of nu? Well, t is my Brownian map, so push forward. So t of x has law nu, and so if I sample x and y IID from mu, if I apply t of x and t of y, then these are two IID samples from nu, and therefore expected value of wtx minus ty is f of mu. Same deal here. 1 minus tx plus t times capital Tx gives me a sample from rho t. 1 minus t of y plus t times capital T of y gives me a sample from rho t. I combine the two, I get this. And now you see, it's neatly of this form 1 minus tx minus y, t times tx minus ty, and therefore its W is convex. I get convexity. Make sense? Same way you just generalize geodesic convexity. Good. So a question that we can ask is, what about strict convexity? So in the first example, which is this potential energy example, we say that potential energy is strictly convex. This is strictly convex if V is strictly convex. If V is strictly convex, the potential energy is actually strictly convex. And this follows immediately from the proof. What do you think is a condition for strict convexity, strict geodesic convexity of interaction energy, which is this guy? So here. Can you come up with a sufficient condition when this is strictly convex? What's your natural guess? You give me a natural guess. I'll show the natural guess. Okay, with 70% chance it's wrong, 30% chance it's correct. But what is your natural guess?
Okay, so hopefully I'm not in the 30%, but I'm guessing maybe W has to be strictly convex.
Right, so if W is strictly convex, that's your natural guess that your interaction energy would also be strictly convex, and this is wrong. And why this is wrong? Well, it just comes from this formula here. This formula is actually invariant if I replace xi by xi plus any constant. Because I'm taking xi minus xj, right? So it doesn't, the way to remember is that sample variance does not depend on mean. If you shift the mean, I always get the same sample variance. So if I change the mean of this mu by adding a constant to this random variable, I always get the same interaction energy. So along those lines, the function doesn't change, and therefore it cannot be strictly convex. However, it will remain strictly convex if I fix my mean, as long as W is strictly convex. Good. So that's the observation here. It is strictly, only when strictly, so if W is strictly convex, and when I restrict myself to a given mean, then it is strictly convex. Otherwise, there are always these lines where I shift the mean, and therefore it cannot have any strict convexity there. Same idea, convex, if it is W is convex, is also generalized geodesically convex. Strictly convex, again, if I'm given a mean. Everybody is clear? The most important function for which we're interested in convexity or geodesic convexity is what is called internal energy. Now, what is an internal energy? It looks like this. So if you take a probability measure, which is absolutely continuous, take a function u, which takes non-negative entries to non-negative entries, and actually I will need to assume that u of 0 is 0. So take a function u, which takes non-negative numbers to non-negative numbers, and u of 0 is 0, and you define your f of rho, which is just a density, to be u applied to the density, and you integrate with respect to the Lebesgue measure. And this is the definition of internal energy. They are nonlinear functions in the usual sense for my probability measure rho x, but they're very important. A particularly important example is entropy. So entropy of rho is the integral of rho x log rho x dx. If you have seen entropy or Shannon entropy before, you will see that in information theory, this entropy is what is called differential entropy, and they put a negative sign in front of it. A differential entropy is negative of integral rho x log rho x dx. For some historical reason, optimal transport does not do that. In optimal transport, entropy, just say entropy, don't talk about differential entropy, just entropy, and we don't put a negative sign, it's always integral of rho x log rho x dx. Okay, very, very important quantity, one of the most important physical and mathematical quantities. Entropy is one such thing. Other important quantities are like x to the power alpha between alpha larger than or equal to 1. It comes in other variants of entropy, like Renyi entropy and other divergence functions. We may touch upon them later, but there are many, many such examples where you take the density itself, you just, like, for example, take alpha to be 2, and you can consider what is the integral of rho square of x dx. So that's a second moment of the density. And that's a perfectly valid function of a probability measure. And we can ask, when is this function geodesically convex? Cool. Okay. So I've already done this example. So here is a fact, and this is the main theorem that we are going to learn. The theorem is that the function rho to f of rho, this is geodesically convex if and only if the following function is decreasing convex. So what you do is that you look for every r which is non-negative, so positive actually, from 0 to infinity. Look at the function f of r, which is r to the power d u of r to the power minus d. This function should be a decreasing convex function on 0 infinity, and that's a necessary and sufficient condition that this function of probability measures, this is geodesically convex. Very bizarre when you see it for the first time, but I'll explain to you why physics forces this condition. Okay. A quick example of this is the entropy for the function that comes from the entropy, which is x log x. If I take my f of r, then x will be substituted by r to the power d, r to the power minus d, and I'll multiply by r to the power d. And here, of course, I've done a mistake in my calculations. So forget this. I've done it wrong. So what is f of r? So r to the power d, and then r to the power minus d will go here. So that will be r to the power minus d. And then this is log of r to the power minus d. So r to the power d, r to the power minus d cancels out, and I get minus d log r. Now, log r is a concave function. So minus log r is a convex function. The convexity is fine. Log is an increasing function. So minus log is a decreasing function. The decreasing convex function is fine. And therefore, entropy is geodesically convex. Good. The second example is x to the power alpha for alpha between 0 and 1. So I will multiply, I will take the function applied to r to the power minus d. That will give me r to the power minus d alpha. And I'll multiply by r to the power d, which is r to the power d. So that gives me r to the power minus d alpha minus 1. This is a decreasing function, obviously, because alpha is larger than 1. Also, it's obviously this is convex, so it's a decreasing convex function on 0 infinity, and therefore the corresponding function of probability measures is geodesically convex.
What is f of rho here? Is this still totally general, or
No, so I'm given
something
my
specific
internal
with U?
energy. Right, it's generated
Yeah,
from
it's
U.
this specific one.
So,
Okay, yeah.
yeah, so U is given to me, and I'm defining my f to be, you take the function U, you apply to r to the power minus d, where d is a dimension, and you multiply the whole thing by r to the power d. And now this becomes a function of r, which is dimension dependent. And therefore, if this is decreasing convex, then you are fine. Not, then you are not fine. So certain functions are actually only geodesically convex in certain dimensions and not in other dimensions. Very bizarre.
Oh, interesting.
Is the calculation clear? Do you follow the calculation? Very simple check. But why this condition is necessary in thing is that what I'll go in the next slide. But when you first see it, it just seems very bizarre.
Say that again about how this D connects with the dimension of the problem. I mean, here it
Oh,
just
by
seems like it's
definition, D is dimension. So there are, for example, if you
of
change
X.
this, I've written x to
Got
the
it.
power alpha, for example, for alpha greater than or equal to 1. You can ask the question, what about x to the power alpha for alpha less than 1? Is this function going to be, is the corresponding function going to be convex? Well, it
No.
will be for certain dimensions, but not for other dimensions. And you can do this easy calculation and see for what dimensions this is true.
Oh, interesting. Thank you.
Okay. Why is this condition necessary? This condition is so bizarre. Why is this condition necessary? So I'll try to explain through one particular example. So take mu to be my uniform over my cube, 0, 1 to the power d. And take nu to be uniform over a cube of side length A. I've done this calculation before in my last class, that this is two uniform distributions. What is the geodesic? Well, it's very simple. The map that takes mu to nu is just x. It's just that t of x is equal to a times x. That's an affine function, therefore it satisfies Brunier's theorem. It takes my uniform over the unit cube to uniform over cube of side length a, and therefore my rho t is a push forward by t times a of a uniform, and therefore it's just uniform ta to the power d. So it's our cube with our side length of t times a. Right, so look into my slides from the previous class, we did this example. And so if I compute what is my my f of rho t, well, now this is very simple because a uniform distribution
Isn't there a
has
little
a con.
mistake? Isn't there a little mistake there because it's supposed to be like 1 plus something because it will shrink back down to 0 and go up to A. Doesn't it have to go in between 1 and A, the upper bound?
Yes, thank you.
It was something like 1 plus 1 minus t times A or something.
So tt, this is going to be 1 minus t of x plus t times ax. And so then this is going to be, yes, right. So then this is going to be, so yeah, this is going to be from 1 minus,
I think the lower might be good.
I think the, okay, so I'm taking my uniform distribution, I'm plugging this in. So tt of x, well, this is always between 1 minus t, and this is between t times a. And so this is between 1 minus t and t times a. 1 minus t times ta. I think this is correct. So if I take 0, okay, I'll correct this something. Just have I did a typo here. Something is 1 minus t and t should be there. No, I'm doing something wrong here. This is 1 minus tx, not 1 minus t. So this is 1 minus t x plus ta, and so I get so yeah, so this is 1 minus t plus ta x. Okay, good. So then this is not ta, but 1 minus t plus ta. Thank you. So this is really, this is not ta, but 1 minus t plus ta. Okay. That's my side length. And so, okay, so there's probably some typos here too, but the idea is still the same. If I compute my f of rho t, then this is my uniform density, and uniform densities are constant. So I've done this computation with uniform 0 ta to the power d, but should be able to do this for the other case as well, just by switching ta to be minus t plus ta. And so what I would get here is that this is my uniform over this constant density, being integrated. Now, where is this being integrated? This dx is being integrated over the cube. This is over the cube. And so what is the volume of the cube? That's ta to the power d. I'm still using ta here. You have to make the change for the other one. What is the density? Well, it's 1 over ta to the power d, and that's why I get this function. And so over the geodesic, I get the function, which is ta to the power d, u of ta to the power minus d. And so if over this geodesic, this has to be convex, then this function must be convex. Clear? So this is a particular geodesic that I'm joining between mu and nu. And over that, things are simple. My density is a constant. So I can just write down my full density. And so if it has to be convex, then this must be convex. And so that's how you get this condition. I'll correct it with the proper 1 minus t plus ta. Is the idea clear? Why is this condition sufficient? The condition is sufficient because of a very standard probabilistic approximation, which is that I can approximate any arbitrary density by disjoint uniform distributions. How? Well, if I have any density, I can always pick some empirical distribution, delta of xi, I equals to 1 to n, that approximates this density. But this is, of course, not absolutely continuous. So I have these points, x1, I have this point, x2, x3, they are kind of atoms. And now you pick tiny cubes around these atoms, and you fill them up with uniform density. And so if I look into 1 over n, delta of uniform around these xi's, then that's an absolutely continuous distribution, which will approximate this density. This is the basic idea behind what you call in statistics the kernel density estimation. You take these points and you just put this kind of little bit of kernels around them, make them smooth, and that's always an estimate of the density. Here, these kernels have little bits of uniform. So you make these uniforms, and you make these uniforms to be disjoint. And once you make these uniforms to be disjoint, look at this function here. This function simply becomes the sum over each one of these uniform components. And so if you understand what is happening for the uniforms, then you can do for the whole problem. And that's how the problem goes. The only kink in this argument is that when these uniforms are actually getting transported by a Brenier map, they are not getting uniform to a cube, they are getting uniform to some parallelograms. And this distortion is coming from the determinant of the Jacobian of the Brenier map T. Right? If I take a tiny bit of uniform on a cube and I transport it, I don't get a cube anymore. I get a parallelogram. The sides are tilted, and the sides are tilted by the eigenfunctions of the Jacobian of the map that I'm using to transport it. And so somehow that has to be corrected for, that doesn't create a problem. And so a crucial part of the proof uses the following well-known fact that if I take on the convex cone of symmetric positive semi-definite matrices, d by t symmetric positive definite matrices, the function that takes a to the determinant of a raised to the power of 1 over d, this function is actually a concave function. This is a well-known theorem in optimization in linear algebra. This particular fact is used to correct for this distortions of the cubes as I send them over by my Brenier map. Okay, why do I always get symmetric positive definite matrices? Because this T map is actually given by the gradient of a function, convex function phi. And so the Jacobian of this function T is nothing but the Hessian of the convex function phi. The Hessians are positive semi-definite and they're symmetric. And so once again, the fact that Brenier's theorem characterizes these as gradients of convex functions is used critically in this proof. Good. Okay, so I won't go into the details of the proof. The textbooks have the details, but this is the idea. You reduce it to a bunch of uniforms and you correct for this distortion. A quick consequence of this is that this is why McCann originally devised this concept, is that if I have any function which is like a sum of these three quantities, some what is called internal energy, potential energy, and interaction energy. If I assume my V is strictly convex, my W is convex, and U is one of the satisfies that R to the power D to U of R to the power minus D is decreasing convex, then this function is strictly geodesically convex. And if I have a strictly convex function, it can have at most one minimizer. And so any such function that you can construct has at most one minimizer. So a quick example of this is Kullback-Leibler. This is a very important function. Take rho infinity to be e to the power minus v. This is my density, and assume that this density is a log concave density, which means v is convex. A Kullback-Leibler divergence or relative entropy is the following function. For any rho, the function is that f of rho is the integral of rho x log rho x over rho infinity of x. And if you simplify this, you get that this is the entropy of rho plus this linear function vx rho x dx. Now, this is exactly of this type, where U is the internal energy's entropy, V is this object, and W is 0. And it says this has at most one minimizer. But we don't need this. We already know that Kullback-Leibler has at most one minimizer, and that minimizer is just rho equals to rho infinity when this is strictly 0. Otherwise, it's always strictly positive. And so if V is strictly convex, so it's a strictly log concave density, this function is strictly geodesically convex. And this is a fact that we'll use later. Okay. All right, so I've run out of time, so I'll skip the last part, and then I'll see you next time. And here next time means there is no class on Friday, there's no class on Monday. Happy Thanksgiving to all my Canadian listeners here. So next week, Wednesday, is when we next meet. Good. Any questions? But the class is over, so you guys can leave unless you have any questions that I can answer.
I was just trying to think of in the materials, like convexity of potentials, like a lot of the potential I've seen in biomolecular simulation and material science.
Mm-hmm.
They have little close to kind of equilibrium. They're probably convex, but then you go away and there's always like a lot of curvature. And
unfortunately, that's true. And that makes this, of course, that's why those problems are difficult. So so you can talk about local convexity. You can talk about, okay, this is a common thing that happens in optimization when you use Wasserstein geometry, is that you require this convexity to converge to the minimizers. Like say you want to simulate something, you want to converge to the minimizer. And the theorems would say, well, if your initial guess is in a certain delta neighborhood of the minimizer, then you can converge, but otherwise you can't. There's no guarantee. And so, but this is the landscape of all difficult optimization problems.
Yeah. Okay, thanks.
Any other questions I can answer? Okay, all right. Okay,
I was wondering if it would be
sorry, go ahead.
possible to do. I was wondering if it would be possible to do an online office hour at some point. I'm a remote student, so I can't attend either the UBC or UW.
Yeah, actually, maybe
office
that's
hours.
Well,
it makes you feel better. We haven't had any office hours in UBC, so you don't miss anything.
Yeah, maybe I should just get rid of my in-person office hours because nobody's showing up in my in-person office hours, and just make it online fully so that people can come. Let me think about it. Maybe I'll do it. The problem is that, people are from different time zones. I don't know what time is good for them and so on. So maybe I'll vary the times and do something online, fully online. Okay, thank you. I'll probably do that. Just skip my in-person office hours fully.
That
Thank
would
you
be
very
great.
much.
Thank you.
Okay, anything else? All right, okay. See you guys later. Bye-bye.